Welcome to this lesson on air valves. Air valves have the potential to be an effective and inexpensive form of surge protection when used in the right situations. Today, valve suppliers offer a wide range of air valves, some of them designed for special situations. As a result, engineers need a solid understanding of air valve basics and how the operation of air valves is related to transient analysis and surge protection of pipelines. Rather than attempting to cover the full range of air valve types, this lesson aims to build your understanding of just two frequently used types. This lesson describes the transient behaviour of air valves and how they are modelled by the WATAM transient analysis software. Here are the two types of air valves found in common use. On the left, we are looking at the traditional older style of air valve, often referred to as kinetic air release valves in industry literature. They are constructed with a buoyant ball that floats up against an air escape orifice. They come in single and double chamber formats. The picture is showing a double chamber air valve. In the WATAM software, this type of valve is referred to as an air valve. In recent years, a new design has appeared which employs multiple buoyant cylindrical discs rather than buoyant balls. These valves are sometimes referred to as anti-shock air valves in industry literature. WATAM refers to these valves by the proprietary name Ventamat air valve. It is important to have a clear understanding of how the two types of air valves operate and how their different modes of operation affect a water system's surge behaviour. A normal air valve is built with a simple buoyant ball. While fluid is present, the ball floats upwards and seats against an orifice at the top of the air valve. As small amounts of air accumulate in the air valve, the air escapes around the ball and through the orifice at the top of the air valve. Normal air valves have a significant disadvantage because they tend to leak water in locations where the prevailing operating head is less than 10 metres. When placed at critical low head crests along a pipeline, the buoyant ball air valve design tends to leak. History has proven that system operators turn leaking air valves off. This is a significant disadvantage if the air valve is required to provide surge protection to the pipeline. In comparison, the multi-disc design is typically built with 3 discs, each designed to perform a different function within the air valve. These valves are far more flexible in operation because they have multiple orifices which can discharge air at different rates. As small amounts of air accumulate in the valve, it affects the buoyancy of the bottom disc in the valve. This allows the bottom disc to drop slightly, exposing a very small orifice and seat in the second disc. Accumulated air escapes through the exit passage available through the second and top discs. This multiple disc design performs very well at low operating heads without leaking. This is achieved because the multiple disc air valves are designed to operate in several modes, tailored to discharging accumulated air, admitting air into the pipeline, discharging large volumes of air from the pipeline, or closing when water returns to the air valve location. To demonstrate how these differences in air valve design influence transient behaviour, let's walk through the sequence of valve operation during a negative head surge event. When a normal air valve is required to admit air, its buoyant ball drops and air flows through the valve body around the ball. When a multiple disc air valve needs to admit air, all of its discs drop and air flows through the body of the valve around all 3 discs. In this mode, sucking in air, both air valve types behave the same way. When a normal air valve experiences reversal in the direction of the airflow, that is, surge heads and water velocities in the pipeline have reversed, and the valve starts to release air, the ball stays down until the critical air velocity is reached. Multiple disc air valves behave similarly. In this mode, all discs stay down until the critical air velocity is reached. In a normal air valve, when the critical air velocity is reached, the ball shuts, totally sealing the valve. In multiple disc air valves, when the critical air velocity is reached, only the top disc shuts. This puts a multiple disc valve into a different operating mode. Air is now able to escape through a small passage through the middle of the top disc. In this mode, the rate of discharge is reduced. This means the fluid's approach velocity towards the air valve is reduced. It is this mode of operation, a reduced fluid approach velocity, that leads to this type of air valve being marketed as an anti-shock air valve. Yet the surge event and sequence of air valve operating modes doesn't end there. The fluid still has to reach the air valve location. In a normal air valve, its ball closes rapidly at the critical air velocity, trapping air in the pipeline. As a consequence, normal air valves form an air cushion in the pipeline. As the fluid continues to approach the air valve, air in the cushion is compressed, which dampens the rate of velocity change in the pipeline. In comparison, in a multiple disc air valve, when the fluid arrives, the bottom disc closes. Swapping into this mode of operation instantly reduces the velocity in the approaching water column to zero. As a result, a multiple disc air valve may create a minor spike in head when the fluid reaches the air valve location. WATAM simulates these differences in transient behaviour between normal air valves and multiple disc air valves. WATAM users need to understand these differences and match their selection of air valve type to their specific project requirements. Users have often asked why so-called anti-shock air valves give slightly worse simulated surge results. It is because both types of valves close fully and instantly at some point in their operating sequence. One type does this with air trapped in the pipe, and the other type, marketed as anti-shock, does not.